For the second example, we're going to look at a situation where two gears are connected. We'll say the smaller one is driving the bigger one. I guess it really doesn't matter. The smaller one has a 5.6 centimeter diameter. The bigger one has a 12.5 centimeter diameter. And so what we need, what I'm looking for here is I'm saying the smaller gear rotates through an arc of 200 degrees. The question is, what arc or what angle is rotated through on the bigger gear? Okay, so we don't know the angle that the bigger gear rotates through when the smaller one goes through a 200-degree angle. Okay, so the principle behind this, when the two gears, of course mine look like sunshines or something here, but the teeth on the gears, as they rotate, no matter how big they are, as one rotates the other one, the arc lengths that they go through are the same. So even if it's a smaller gear and a bigger gear, as they rotate, the arc lengths, because the edges are in contact with each other, they're going to swipe out the same arc length. So what I could do is really set up two equations that have the S equal R theta, because we're dealing with the arc length again. In this first gear, I'm going to call it S1 equals R1 theta 1. I'll call this gear 1. In the second gear, I'll say S2 equals R2 theta 2, okay? Well, what's interesting between these is I just said the S's, the arc lengths, are the same. They trace out the same distance. And so if S1 and R1, or I'm sorry, S1 and S2 are equal to each other, then we could do a substitution, and it must be the case that R1 theta 1 is equal to R2 theta 2, okay? Now, this will work, again, these formulas really only work if we're in radian measure. Due to the scenario here, the way that the two equations are equal to each other, this actually does work out in degree mode, like a calculator, in degree form, or with degree units. But I'm going to go ahead and go through the conversion because I think it's valuable for you guys to practice that. But it will actually work out if I plug the 200 in here. So, but I'm going to go ahead and convert that. So 200 degrees multiplied by pi over 180 to get my radian measure. Again, I'm going to chop off the zeros and divide them both by 10. That reduces this down. I get 20 pi over 18. And of course, I could reduce further. If I divide them both by 2, I would get, what's that, 10 and a 9. So it's 10 pi over 9. So 200 degrees is really 10 pi over 9. So I'm going to go ahead and substitute that into my equation along with, well, these two measurements are diameters. I don't have radius yet. I've got to convert those into radii. So cut them both in half. The 5.6, if I cut that in half, what's that, a 2.8 centimeter radius. And the 12.5, if I cut that in half, that's 6.25 centimeter radius. Okay, so now I can put those two measurements into my formula for R1 and R2, along with 10 pi over 9 as my angle measure, theta 1. Okay, so I'm going to put all that stuff in. So R1 is 2.8. Theta 1 is 10 pi over 9. R2 is 6.25, and theta 2 is what we don't know. That's actually our question mark up here, is the angle for the bigger gear. So I'll just substitute in theta 2. Our goal then is just to solve for this theta 2. So I'm going to divide both sides by the 6.25. And that should pretty much get us there, just typing it all in the calculator. Now I'm going to type this in stages. And again, I'm going to round this off probably to 1 decimal place. I don't think I want to get any better accuracy, because if I go to 2 decimal places, these measurements were not originally measured that accurate. So we'll keep it in the same original accuracy. So I'm going to type in 2.8 times 10 pi. Where is it? 10 pi divided by 9. Okay, so you can kind of see 2.8 times 10 pi over 9. The pi, if you need to know where that is, it's the second, and then it's this little caret or exponent button. So second, and then that will give you the pi. So that gives me part of it. And then I'm going to divide that by 6.25. So I'm just going to hit the divide button, and I'll take my previous answer, divide by 6.25. Yeah, I get about 1.56, 1.6. Let's call it that. So it's approximately 1.6. And now this is in radians. 1.6 radians, right? So I'm all converted into radians. Now what I want to do before I clear this out, I'm going to utilize my decimals and convert this back into degrees. Okay, so if I do that, I would have to multiply by 180 over pi. Okay, so that's what I'm going to do. I'm going to hit the times, and then 180 divide by pi. That gives me about 89.6 degrees on the dot. So I'm going to go with that, 89.6 degrees. Now, it's kind of nice. It worked out well. So it's just a hair under a 90-degree angle would be swiped out by that bigger gear. It's kind of interesting. But again, just to point this out, I could have done this whole problem without that unit conversion and just kept everything in degrees right off the bat. The gear problems like this, and there's a couple of them in the homework, you don't actually technically have to do that step. It is a lot simpler to avoid it. I'll just show you real quickly what would have happened. So R1 is 2.8. Theta 1 was 200. R2 is 6.25. And then theta 2 we didn't know. If you just go and type this, well, of course you divide by the 6.25. But if I just type that directly into the calculator and go with 2.8 times 200, and then divide that, see if I can get that to focus there, divide that by 6.25. $89.6. Check that out. That worked out really nicely. So it's actually a little faster to not use the radians. Again, that only works when you're setting 2 different arc lengths equal to each other. In the pulley problem you saw in the last video, this will not work to leave it in degree mode. You don't want to do the degree mode. I'm just saying it like it's a calculator again. To leave it in degree units, it won't work. So you want to keep the theta in radians in pretty much all other examples, except for this where the 2 arc lengths are the same.